water sources and contamination, evaluation of water or water quality. Water source and contamination, evaluation of water or water quality. Topic: water source contamination and their prevention. Water quality or evaluation of water, physical, chemical, biological and bacteriological. Water source contamination and evaluation. Water source. Water source. Water is indispensable to support life and to help in the productive process of animal. Water is also needed for many other operations in the farm to maintain the cleanness of animal and their habitation and to process many of the animal products like milk, butter, cheese and meat. Water is also needed for cleaning various utensils used in the handling of animal products. This aspect has a direct bearing on public health. Hence, the water supply should come from standard. Lack of knowledge on the quality of water and its source will bring down the efficiency of farm management, leading to general breakdown in the health and production of animal. The natural source of water: rainwater, surface water, brooks, stream, river, lake; underground water, subsoil water, deep groundwater, spring. Rainwater. This is precipitation of water which is obtained as the condensation of moisture in the form of rain, snow and dew. The amount of rainwater depends upon the rainfall and the distribution of rain over a period in particular region. The two monsoon, the southwest and northeast monsoon, bring about 80% of total rainfall. The rainwater must be collected in suitable nature basin or artificial reservoir and stored as a source for use in the farm. Rainwater as its origin is the least polluted water with minimum impurities, but as it descended down it gathered various impurities or pollutants depending upon the activities of the region. Rainwater collected under the rural conditions is less pollutant than that collected under the urban condition. Rainwater collected from highly industrialized places are heavily contaminated with toxic matter or harmful matter. In general, rain water is comparatively pure and is soft in nature with less of dissolved impurities. It is insipid in taste and sometimes it will acidic in reaction, having flumogosolvent characters with corrosive properties. Surface water. Surface water is the natural collection of rainwater that has fallen on the earth, washed the surface and collected in the form of river and lakes. These are most common and economical sources under natural farming conditions where there is a good rainfall. In the absence of good rainfall, most of these sources will be dripped up. Surface sources in general provide a poor quality water. Sometimes the water may be dangerous, polluted by manure and land washing. The quality of such water changes due to the influence of rain and sun. The lake water is highly impure even when it is freshly collected. The river water is least populated as its origin, but as it travels, it gathered impurities in the form of land washing and household sewage and various industrial effluent discharged into the river. Pollutant river water, when it travels more distance, it undergoes certain amount of self-purification due to natural sedimentation, absorption of oxygen and oxidation, percolation into the beds and reappearing in the form of spring. The exposure of vast sheet of water to the ultraviolet ray of the sun is also responsible for self-purification. The mineral content of the river water depends upon geological strata of the earth through which the water flows. The chemical characters of river water is suitable subject of wide variation according to the nature of the gathering ground and also to to the different geological formation through which the river bed passes. Dissolved solid take up in one arm may be disposed in another area. The bacterial quality of water dependent upon the amount of water pollution taking place and the change given for self-purification of water. Hygienic measures should be taken for the protection of surface water source to prevent pollution and contamination by preventing the mixing up of industrial waste water from livestock farm and dwelling place. Public Health Act as well as River Pollution Prevention Act should be enforced. Undue pollution with sewage industrial effluent should be checked. Gathering ground or catchment or such as lakes should be protected by high-raised wall or fencing, preventing unauthorized entry of livestock and human beings and should be maintained as per the public health regulation. Underground water. The water is held beneath the soil and it has to be tapped in the form of wells or springs. Two categories of underground water, two categories: subsoil water, deep groundwater. Subsoil water. This water is held above the first impermeable layer and it rises and falls according to the season and rainfall of the locality. The subsoil water is liable to gross contamination from organic vegetable waste and livestock secretory pollutant. The fitness of the subsoil water as a source for the livestock should be regarded with suspicion and such water had to be submitted to bacteriological examination before put the use. Deep groundwater. This water lays below at least one impermeable stratum as it has percolated to a greater depth. It is usually free from significant bacterial pollution. Water is protected from surface pollution by the presence of impermeable strata. Even this groundwater source may occasionally be grossly polluted and contaminated due to certain natural faults such as cracks and fissures in the course of rock formation. Mineral content of groundwater is generally very high. Springs. These are natural outlets of underground water and they supply the water at the surface of the earth in the form in different springs. Land spring or deep spring, intermittent. Whenever there is a dip in the land exposing the impermeable stratum to the surface, the water comes out in the form of land spring. The water is doubtful purity and its supply is seasonal. Fissure spring. This spring occurs due to the presence of deep fissure or crack in the rock up to the water-bearing stratum. Junction spring. This spring results from the geological fault occurring due to two different strata coming together and forming a junction. Deep groundwater come out in the form of a spring at the junction at the strata. The last two springs are permanent springs supply good quality water with larger seasonal fluctuations. These natural springs can be developed into good water source. An artificial basin should be collected for such water. Fans should be provided all around to prevent unauthorized entry of human being and animal. The quality of water is similar to that of the deep underground water. Classification of water. Classification of water according to their palatability and wholesomeness is also spring water, deep water, upland surface water, store rainwater, water from cultivated land, river water, shallow well water. Water contamination. Sewage from unsewered area, faulty municipal sewerage system, storm water runoff, industrial effluent, agricultural leachate from household and industrial solid waste, and infiltration of fertilizer and pesticide from agricultural area. The household effluent are discharge into open survey, which often infiltrate into the surface water source. Deficiency in the sewage system, such as overflow of untreated sewage from deficient pumping station and clogged sewerage pipeline. Leakage from badly maintained sewerage pipeline are major pollutant source, and clogging of sewage often occur due to uncontrolled dumping of soil waste. In many places where sewers are connected to the storm drain, they result in contaminated water source. In generally, many drains are silted up and choked with vegetation. Thus, large area, particularly the low-lying area, are flooded during rainy season and water stagnates for several weeks after the rain. This may result in contamination of potential groundwater. Furthermore, the washout of accumulated water and debris from the storm drain during the rainy season result in pollution of sediments in the surface water near the outfall. Non-treated or poorly treated wastewater from the textile plant, tanneries, distilleries, leachate from hazardous waste, example fertilizer, petrochemical and caustic soda plant also contaminated the water. Agriculture, due to uncontrolled use, that significant amount of fertilizer and pesticide infiltrate to the surface water. Main source area and possible source: sewage system. Lack of system is in UN sewered area, slum area. Leakage and overflow from the sewerage pipeline. Overflow from deficient pumping system. Inadequate sewerage treatment facilities, inclusive pipelining and pumping station for treated wastewater. Stormwater overflow from drainage with wash out of accumulated industrial effluent. Inadequately treated industrial effluent, leakage and spillage of chemicals, irrigation water from distilleries and textile plant. Municipal solid waste, leachates from inadequate collection facilities, uncontrolled dumping site and unprotected landfills, uncontrolled dumping into surface water and sewerage. Industrial solid waste, inclusive of hazardous waste, leachates from on-site storage, uncontrolled dumping site and unprotected landfills. Energy plant, leachates from coal, cinders and fly ash. Agricultural infiltration of fertilizer and pesticides, seawater or exploitation of groundwater tidals, evaluation of water or water qualities. Physical, chemical, biological and bacteriological evaluation of water are discussed. Physical evaluation of water. Water sample is evaluated physically for color, turbidity, odor, taste and electrical conductivity. Color and turbidity, odor and taste, electrical conductivity. Color and turbidity. Natural water rarely show color other than yellow or reddish brown, which usually indicate the presence of peat acid or, in the case of turbid water, suspended particle clay or iron oxide. Occasionally algal growth is responsible for the appearance of a green or red color. Few water which can be considered satisfactory contain appreciable quantities of suspended organic matter. Its presence in any quantity encourages the growth of microorganisms, render the water difficult to filter, and frequently make sterilization difficult. Suspended mineral matter, on the other hand, is less objectionable. Its presence tends to be seasonal, occurring usually after a period of heavy rain, although when in the form of hydrated oxide of iron, it appears as a permanent turbidity in ferruginous water. Odor and taste. Odor and taste can only give an indication of sewage contamination if it is excessive, but they are useful in detecting other unusual type of contamination which are difficult to detect chemically. For example, the accidental contamination with a small quantity of paraffin oil or similar substance sometimes occurs. Chemical method may not be sufficient sensitive to detect trace of these compounds, and in such cases taste and smell may be the only guide to the presence of these contaminants. Petty water nearly always have a slight odor. Certain water contains sulfated hydrogen. Decomposition. Aquatic fauna and flora in several servicemen are not infrequently the cause of smelly water. Rainwater has a flat insipid taste. Soap water taste soft. Ferruginous water taste of ink. Water containing much sodium chloride have a brackish taste. The water from newly laid men may have a terry flavor. Water treated with bleaching powder test for chlorine if the available chlorine in the water exceeds 3 of 4 parts per million. Hard water and also those containing nitrate and carbonic acid are more palatable than soft water of those free from gas in solution. Electrical conductivity. Chemical pure water is a non-conductor of electrical, but the solution in it of ionizable salt renders it conducting. The case with which an electric current is transmitted being directly proportional to the concentration of ionizable salt in solution. This fact is made use of in the examination of natural water, the electrical conductivity of the water being an indirect measure of the amount of dissolved substance present in it. It should be noted that by itself the electrical conductivity gives no indication of the nature of the substance in solution. Value of electrical conductivity for natural water vary from about 100 gamho for soft water dried from the older crystalline rock to about 2000 for very hard water dried from the newer and softer rock. Seawater has a conductivity of about 50,000 ohm. In the absence of sodium salt, the electric conductivity is proportional to the hardness. 1 degree of hardness rising the electrical conductivity by about 20 units. Thus, such a water with a conductivity of 5000 units would possess a hardness of approximately 250. The determination of electrical conductivity finds its greatest use in indicating change in the amount of dissolved solid present in a water where the composition of the dissolved solid fraction is known and is fairly constant. Chemical evaluation of water. The complete chemical examination of water in respect of its susceptibility or otherwise for drinking and for ordinary domestic use normally include determination of total solid, pH, hardness, free and albuminoid, ammonia, nitrate, nitrite, chloride, and action of on metal. It may also be necessary to examine water for unusual constituents such as lead, zinc, arsenic, copper, iron, aluminum, magnesium, fluoride, and cyanide, whose presence may be suspected from a consideration of the source of supply or from a history of toxic symptoms arising in man or animal drinking the water. We list the chemical examination of the interpretation of the result falls strictly within the province of the experience analysis. Some knowledge of the procedure involved will greatly add the pattern researchers in appreciating the significance of the analytical finding. Total solid pH value, hardness, chloride, the nitrogen constituent, reducing powder or oxygen absorbed. Total solid. The method of determination employed is briefly as follows. The reduce left after evaporating a measured volume of water is weathered and the result calculated 2 parts per 1 lake of water. The estimation is usually carried out on filtered water if appreciable quantities of suspended solid are present, so that suspended solid are reported separately from dissolved solid. The residue consists of all the non-volatile substances which were present in solution in the original water. The organic content of the residue can be assessed from the appearance of the residue after genital ignition. Considerable charging indicating a high contact of organic matter. Satisfactory water rarely contain more than 80 parts per 1 lake of dissolved solid, and for most purposes should contain much less. They rarely contain more than a mere trace of organic matter. pH value. The pH of natural water is of importance chiefly from the point of view of possible corrosion of metal. Water with low pH value, especially if the acidity is due to dissolved carbon dioxide or to humic acid, are potentially plumbo solvent. They corrode most metals to some degree. Alkaline water, particularly if the alkalinity is due to dissolved sodium carbonate, are corrosive of zinc. It should be pointed out that water which are natural in reaction are not necessarily non-corrosive. Example, natural solution of chloride and nitrate will corrode most metal. The pH value of a sample of water should therefore be considered along with other determination. Particular hardness. The hardness of water refers to its soap destroying power and is due to the presence of calcium and magnesium salt in solution. It is usual to distinguish between water that are temporarily hard and those that are permanently hard. Temporary hardness is due to the presence of the bicarbonate of calcium and magnesium in solution. Permanent hardness is due to the chloride, sulfate, and to a lesser extent the nitrate of calcium and magnesium. Hardness, whether temporary or permanent, is expressed as part of calcium carbonate per 1 lake part of water. Degrees of hardness are numerically equal to part of calcium carbonate per 1 lake part of water. A total hardness of more than 30 is sufficient to render a water suitable for most purposes, although if required for drinking only a considerably higher hardness might be tolerated. Water with hardness less than 5 are very soft, and such hardness value should be considered along with pH value for possible plumbo-solvent action. Chloride are rarely absent from natural water, being present chiefly as sodium chloride with occasionally magnesium, potassium, and calcium chloride. The chloride content of water derived from rock near the sea is invariably high. Water from deep well may contain sufficient to impart a brackish taste. The presence of chloride considered alone is therefore a little significant as regard hygienic quality, but as sewage contain appreciable quantity of it. If the chloride is present together with free ammonia nitrate or appreciable quantities of nitrate, this finding may support an indication of sewage pollution. Uncontaminated surface water, except near the sea, rarely contain more than 2 parts of chloride per 1 lake. Well water may contain considerable greater quantity. The nitrogenous constituent. The nitrogenous constituent uncontaminated water supply are rarely completely free from nitrogenous constituent, and in such water nitrogen may be present in the form of humic acid or nitrates. Waters contaminated with sewage or other decaying organic matter may contain, in addition to this, ammonium salt or easily decomposable amide and nitrite. As ammonium salt and nitrite are quickly oxidized in natural water to nitrate, their presence is taken as a strong indication of recent contamination with sewage. Quantitatively, the ammonium salt and easily decomposable amide are estimated by distilling a sample of the water made alkaline with sodium carbonate. The amount of ammonia distilling of is estimated calculated to part per 1 lakh and reported as free ammonia. Humic acid and the more complex nitrogenous compounds such as protein do not liberate ammonia on boiling with sodium carbonate but do so when distilled with an alkaline solution of potassium permanganate. The ammonia is estimated calculated to parts per 1 lakh and reported as albuminoid ammonia. Satisfactory water rarely contains any free ammonia at all, and the presence of more than 0.005 parts per 1 lakh must be regarded as significant of pollution. If the amount of free ammonia present is greater than the amount of aluminoid ammonia, then sewage contamination is certain. Many satisfactory water, for example PT water, contain appreciable quantity of aluminoid ammonia, but such water yield the aluminoid ammonia slowly, and they contain only trace of free ammonia. In water other than moorland water, the albuminoid ammonia may be significant of sewage pollution if it is present in concentration greater than 0.01 part per 1 lakh. The presence of nitrate is of no significance in the absence of other nitrogenous constituent. If on the other hand, free ammonia is present, then the presence of nitrate is an added indication of pollution. Reducing power or oxygen absorbed. Reducing power or oxygen absorbed. The pollution of natural water is invariably accompanied by an increase in the amount of organic matter present in solution. The dissolved organic matter is easily oxidized, and the amount of available oxygen absorbed by the water from a oxidized solution give a measure of it. The ability of water to reduce a dilute solution of acid potassium permanganate, referred to as the reducing power or oxygen absorbed figure, and is reported as part of available oxygen absorbed per 1 lakh part of water. Many natural water contain dissolved organic matter that is innocuous. Moorland water, or for example, contain peat acid, and if the reducing power powder of such water is not in excess of about 0.1 part per 1 lakh, they may be regarded as satisfactory. On the case of other water, the reducing power should not normally be in excess of 0.05 part per 1 lakh. In all cases, the reducing power should be considered in the light of the other estimation, for example free ammonia and chloride, that indicate possible contamination. Biological evaluation of water. Biological evaluation of water. All natural water excepting possibly some of the deepest underground water are inhabited by a diverse plant and animal life. The chief phyla of the former being algae, fungi and bacteria, whilst the animal kingdom is represented by protozoa, sponge, rotifers, mollusks, various free-living worms, insects, fishes and amphibia. The kind of plant and animal found in Any particular water depends largely on the character of the water and one the source from which it is drawn. And as far as contaminated intestinal bacterial of human or animal origin are concerned, on the degree to which the water has been exposed to sewage and or manurial pollution. In general, the flora and fauna of surface water are more abundant and more diverse than those of underground waters, whilst those of depressed subterranean water are relatively poorer than the life of subsoil water. A few minute crustacea feeding on bacteria and fungi are able to live in deep well and in the subterranean water on which they draw. But if the well be of great depth or are poorly aerated, the water will usually be devoid of living things. Few, if any, of the form of life, apart from contaminated bacteria of intestinal origin, which may be found in natural water, would appear to be toxic or harmful to man or animal drinking the water. In the following paragraphs, some account is given of the more important form of plant and animal life which are to be found in water supply and which may give rise to problem during the purification, storage and distribution of the water. Algae. The algae constitute the most ubiquitous form of plant life existing in fresh water. The majority are microscopic in size, but some are visible to the naked eye. Example, the bright green thread-like algae often seen in pond and stream. From the point of view of water supply, three groups of algae are of great importance, namely the isocyanate or green algae, the myxophyceae or blue-green algae, and the diatoms. This and other group of algae which may only flourish moderately in the running water of rivers and streams, generally increasing markedly in the comparatively still water of lake and storage reservoir. This increase is useful in some way. The aeration of the water by the algae helps to purify it, and as will be mentioned later, they play a vital role in the purification of water supply by filtration process. But if their growth becomes excessive, they may interfere with filtration. Such excessive increases in the algae population of open storage reservoir can be controlled by the application to the water of a chemical algicide, such as copper sulfate, which is used at the rate of 1 kg to 4.5 kg CuSO4 per 45,46,000 liters of water. Care must be taken to ensure the even distribution of the CuSO4 throughout the reservoir. The usual method of application is to tow a bag of the along careful plant lines in the reservoir. It is better policy to use CuSO4 as a preventive against excessive algal multiplication in a reservoir than as a curative, in which case the dead algae undergoing decomposition may render the water unfit to use for a time. Objectionable tests due to algae growth may be removed by dousing the water with powdered activated carbon at the rate of 1 to 5 parts per million. The covering over of small reservoir will effectively reduce algae growth. Therein, a great bulk of algae passing on from storage reservoir to the filter bed during period of algae abundance introduce mechanical difficulties in the filtration of the water, and unless the filtration plant is frequently cleaned, the filter bed will become choked. The use of algicides in the filter bed is not practicable as the purification of very large quantities of dead algae may be even more objectionable than the presence of the living plant in the water. If it is necessary to remove offensive trash after filtration, about 0.5% part per million of potassium permanganate may be used. Soil bacteria. Soil bacteria. Groundwater lying near the surface will usually contain free living bacteria derived from the upper few inches of the soil complex. These bacteria include aerobic form, which break down organic material into the simple compound element of carbon, nitrogen, and hydrogen. This resolution process is further carried on by two groups of nitrogen oxide organisms, which convert ammoniacal nitrogen to acid radicals that, in combination with existing soil base from nitrite and nitrate. The first of these bacterial groups, Nitrosomonas, converts ammonia to nitrite, while the second, Nitrobacter, completes the oxidation process by converting the nitrite to nitrate, which constitutes the completely oxidized state of N2. The bacterial which initiate the breakdown of organic material as well as those involved in the oxidation of nitrogen require for their efficient functioning the provision of adequate moisture, oxygen, suitable bases, and an environmental temperature of over 50 Celsius. Unless these requirements are satisfied, the distinction of organic matter cannot proceed to complete, and the end product represented by the humic acid now formed cause shoring of the soil. Water draining from a soil in which these conditions pertain will be acid in character, as for example, the acid water draining from waterlogged peat accumulation, in which the incomplete breakdown of the excessive amount of vegetable organic matter is due to the absence of oxygen and of suitable bases. The plant remains are finally converted to true peat by anaerobic bacteria. Sandy soil, which are always characteristically low in mineral matter, may also under certain conditions accumulate organic matter because in the absence of soil bases line, the decomposition of plant debris cannot proceed and layer of peat may be formed. Similarly, even on heavy land, plant debris may tend to accumulate. Example, many old grassland have matted turfs many inches thick, which show little or no sign of decomposition if plugged in unless time is used to correct the soil acidity. Another example of failure of this biological scavenging processes sometimes occurs in connection with land treatment of sewage tank liquor, while as a result of excessive application of the sewage liquor, the alkaline base in the solid become exhausted and consequently the conversion of the acid formed by the nitrifying bacteria to nitrate and nitrite does not occur, and they accumulate in the soil, rendering it swagic. Such soil may have its purifying properties restored by the addition of 1 to 2 tons of lime per acre, combined with a period of rest from further sewage application. Iron bacteria. Iron bacteria. Certain of the bacteria have the power of extracting iron from the water in which they live and of depositing it in the form of ferric hydroxide in the mucilaginous sheath with which they are invested. The Oche beds, sometimes seen on boggy moorland streams, are produced by the deposition of the iron impregnated sheath of these bacteria, which sink to the bottom of the stream when the bacteria died. The presence of iron in their surrounding medium is not essential to the life of the iron bacteria, for they can flourish in its absence. The iron seemed to be assimilated by the bacteria, probably in the form of ferrous bicarbonate, along with nutrient material, is oxidized to the insoluble hydrated ferric oxide and is then deposited in this form in the filament sheath of the bacteria. Crinothrix is perhaps the best known of the iron bacteria, though possibly it is not the most widespread. As normally found, it consists of minute filaments attached by one end to some solid object. Each filament consists of a single row of cells, the whole being invested by mucilaginous sheath. Rapid multiplication of crinothrix in supply reservoir has occasionally produced spectacular effect in the water drawn from the servicemen. The water was unusable for domestic supply owing to its bad taste and smell. The effect in water supply system due to Gallionella, another of the iron bacteria, is less striking than those of Crinothrix, but this organism is probably far more widespread. Gallionella forms a slimy coating on the inner surface of iron supply pipe, for which streamers extended into the water. This coating may become so thick that it considerably reduces the capacity of the pipe. Gallionella also play a part in the formation of the hard rusty nodules and incrustations that are commonly seen in water pipe in some area. The exact role of the bacteria in the production of this is uncertain, but it is thought that in some way they accelerated the deposit of rust, probably through their oxidation process. Chlorination of the water is one of the remedies that have been found satisfactory in the control of iron bacteria and the troubles arising therefrom in public supply system. Fungi. Since all free living fungi are self-providing, example derive their nourishment from decomposition organic material. The occurrence of fungi growing in water is evidence of the presence in the water in fusion of the decomposition organic substance and therefore of possible excreted pollution. The number of species of aquatic fungi is small, and of these the only one which needs consideration in relation to the purity of water supply is the association of fungi, bacteria and protozoa, commonly known as the sewage fungus, which may be found in streams and rivers into which sewage effluent is discharged. The appearance presented by this growth is that of a dirty yellow or greyish jelly-like film covering the bottom and sides of the watercolor waterfalls in which it occurs, and which is especially evident where the current is slow or the watercourse tortoise. It may be found growing plentifully in drains which carry off the effluent water of sewage form. Whenever this fungus occurs, it is certain sign of the presence in the water of a large quantity of organic compounds and therefore of possible pollution either with sewage effluent or perhaps with raw sewage. Fauna of water supplies. Fauna of water supplies. Member of all the chief group of freshwater animals are to be found in one or other of the various sources from which water supply are drawn. They may gain access to purification plant at waterworks, but rarely causes serious trouble in these. In the past, before the sun, filtration of public water supply was universally adopted. There are several instances where sponge, polyzoa, and mollusca are reported to have flourished abundantly in service pipe and man. The sand filtration of water effectively excluded the minute larvae stage of this animal type, which can pass readily through the strainer used to stop the grosser inclusion of natural water. Should these larvae, on the other hand, gain access to the water pipe, they may lodge at suitable site and develop into the adult form. The latter feed on diatom and other algae, which are invariably present in unfiltered water and may multiply so greatly as to seriously reduce the capacity of the pipe. They afford lodgement to a whole host of organisms which would otherwise to step on by the current, and when members of this pipe fauna die, their decay pollutes the water and favor the growth of saprophytic bacteria. The common freshwater fishes are usually to be found in sources of water supply such as river and natural lake. They are thought to exercise a beneficial influence on the quality of the water in that they feed on the smaller plant and protozoal forms and so possible limit the number of these. For this reason, artificial improunding reservoir of the storage of water are commonly stocked with fish generally drug. Bacteriological evolution of water. Bacteriological the significance of the result obtained by the bacteriological examination of water supply presupposes a knowledge of the possible bacterial form which may be found in water. This form may be broadly classified into two main groups. Firstly, saprophytic bacteria, which are indigenous to water, are adapted to live and multiply at temperature lower than body heat. Example, at 2 to 20 centigrade, they derive the nutriment from decayed organic matter. These free-living forms are of little importance from the hygienic standpoint, except that their presence in a water in very large number denoted an abundance of organic matter. The second broad group, which may be called the adventitious water microorganisms, are introduced from outside source and incapable of surviving in water for an indefinite period. Amongst these are included bacteria precipitated from the air by rain or snow, soil bacteria washed in after heavy rainfall, and excretal bacteria from human or animal sources. It is with the two last named that the microbiological evaluation of water supply is almost entirely concerned. It has already been mentioned that the present bacteriological technique used for the detection of sewage pollution of water supply are directed to the demonstration of non-excretal bacteria, especially organisms of the coliform group, and to a lesser extent fecal streptococci and Clostridium welchi. The reason for this greater concentration on the coliform bacilli is partially because of the greater case with which they can be demonstrated by culture method, and partially because Clostridium welchi has been found to survive considerably longer in water than members of the coliform group. The presence, therefore, of these organisms along in a water sample may indicate a pollution more distant in time than is the case with members of the coliform group. Coliform bacilli The coliform basically constitute a group of organisms of diverse origin, though natural habitat is the human and animal intestine and named as Escherichia coli. Some of the coliform group appear to have their primary habitat in the soil and on vegetative and may therefore be regarded as saprophytes. These comprised the aerogens and cloacae. The typical E. coli does not normally lead to a saprophytic existence outside the human and animal intestine. It is the dominant organism found in fishes and for the region is commonly referred to as fecal coli, while the saprophytic referred to as non-fecal coli. The observation of various workers suggest that at ordinary temperature, non-fecal coli group tend to survive longer in water than do fecal coli, so factors other than temperature probably play a part in determining the relative length of survival of this organism. Since E. coli does not normally live for any length of time outside the intestinal tract of man and animal, the presence of this organism in water can be regarded as almost certain evidence of recent excretal pollution of human or animal origin. The further significance of the coliform group as an indication of the nature and time of pollution will be returned to later. It may be mentioned here, however, that there is no very satisfactory method at present for distinguishing between fecal coli of human origin on the one hand and those of animal origin on the other. A consideration of the topographical circumstance relevant to the water supply under examination may sometimes help in assessing fecal coli to their probable sources. For example, in the case of surface water where sheep commonly graze the gathering ground and in the absence of any known source of human pollution, the fecal coli isolated from sample are in all probability of animal origin. A similar conclusion may sometimes be arrived at in the interpretation of the bacteriological finding in the case of a well or stream water where the topographical survey on the spot indicate excretal pollution by livestock, and as far as can be seen after careful investigation, there is little possibility of contamination from human sources. Clostridium welchii. Clostridium welchii. Clostridium welchii. This organism is normally an intestinal inhabitant. It is a spore-forming organism which survives for a considerably longer time in water than the coliform bacilli and usually resistant chlorination. Its presence in water indicates that fecal pollution has occurred, and the finding of Clostridium welchii in the absence of members of the coliform group indicate that the contamination is not of very recent date. The chief value of looking for this organism would seem to lie in the detection of remote or intermittent pollution in surface or shallow water supplies, such as those from a pond or a well. Supply from these sources are commonly used on farms and by small rural communities, and their frequent examination by the coliform test is seldom, if ever, practicable. An occasional examination for coliform bacilli might in any case yield misleading results, since these organisms might have died out since the last stage of pollution. In circumstances such as those mentioned, then the demonstration of Clostridium welchii will show that water is subject to contamination and will indicate the necessity of taking steps to eliminate the source of pollution or otherwise prevent it gaining access to the water. Fecal streptococci. Fecal streptococci. Streptococci of various types are present in a number of situations in the human and animal body. In human feces, the most characteristic type is the usually referred to as Streptococci facialis. The value of a bacteriological test for the detection of these organisms in water supply appear to be largely undecided at the present time. Many workers are of the opinion that it added little to the information yielding by the test for coliform bacilli. Other workers, on the other hand, believe that it has a considerable value in assisting the interpretation of bacteriological analysis when the results of the coliform test are irregular or indefinite. Thus, for example, when it is uncertain whether certain irregular type of coliform bacilli are or are not of fecal origin, the accompanying presence of fecal streptococci will constitute presumptive evidence that the irregular coliform type are derived from feces. The coliform test. The bacteriological examination of water supply for organisms for the coliform group comprises the most suitable and the most generally applicable test for evidence of pollution. The complete examination comprises a number of separate procedures by which it is possible not only to demonstrate the presence of coliform bacilli but also to assign them to the subgroup already mentioned. The complete test for coliform bacilli comprises the following procedure: the presumptive coliform count, the differential coliform test, and plate count at 220 Celsius and 370 Celsius. The particular test or combination of tests required for any given sample submitted for examination will be decided by the bacteriological after consideration of the relevant detail pertaining to the circumstance under which examination of the water supply in question becomes necessary. The importance of supplying as full particular as possible when forwarding sample to a laboratory for examination can therefore be readily understood. By the plate count at 220 C and 370 C, the total number of variable bacteria per unit volume of water is determined. Most of the bacteria growing at 220 Celsius are saprophytic type which are non-pathogenic to human being or animal. It may be thought that the plate count at 220 C is immaterial to some extent. This is true, but it may be pointed out that this count afforded some indication of firstly the amount of food substance available for bacterial nutrition and secondly the amount of soil, dust and other extraneous material carrying bacteria with it that has gained access to the water. On general ground, the greater the number of organisms developing at this temperature, the larger is the amount of available organic matter present, and the less suitable is the water for human consumption. The bacteria developing at 370 Celsius, on the other hand, are mainly parasitic or potentially parasitic, though not necessarily pathogenic type derived from soil, sewage, or excretal material and must therefore be regarded as the evidence of the possible presence of pathogenic types such as members of the typhoid paratyphoid group. The presumptive coliform count together with the differential coliform test is by far the most dedicated index of excretal pollution. These tests are carried out on a quantitative basis and the result reported according to the most recent recommendation in the following manner: probable number of coliform bacilli present in 100 ml, probable number of fecal coli present in 100 ml, interpretation of bacteriological examination. The interpretation of the result of the bacteriological examination for coliform bacilli as well as those for the other intestinal bacteria calls not only for careful consideration of all the relevant factors but also for considerable experience in this work. Final decisions have yet to be reached as to the meaning of all the data obtainable in the laboratory, and any conclusion reached must still be to some extent reflection of individual experience and therefore variable. The bacteriological condition of a water too has to be considered to relation to many other factors such as season, nature, and topography of the source of supply, the frequency of examination, etc. The following quotation give the most authoritative information available at the present time regarding the interpretation of result and the hygienic classification of water supply. E. coli is essential an index for recent excretal pollution. The finding of the organism in water in more than minimal number can never be safely ignored. The presence of organisms of the saprophytic group in water in the absence of fecal E. coli may be due either to contamination of the water with soil, contamination of the water with excretal material at the time sufficiently distant to allow fecal coli to die out, contamination of the water with the excreta of a person who discharging the saprophytic organism in almost pure culture. Thus, this must be relatively uncommon. Inadequate treatment of an initially polluted water with chlorine, which has only success in killing of the more susceptible fecal coli. Which of these explanation is correct can be determined only by inquiry into the source and history of the water. The finding of the high proportion of fecal coli among the total coliform organisms is indicative of heavy or recent excretal pollution. On the other hand, a result showing that the majority of the coliform organisms appear to belong to saprophytic group or to irregular type may be regarded as indicative of a slight infrequent or remote excretal pollution, or perhaps if no fecal coli are present at all, of sample contamination with soil that may or may not have been excretally polluted sometime previously. In practice, it is unwise to neglect completely the presence of organisms of the saprophytic group, even though no fecal coli can be found. Their presence may indicate a minor degree of pollution which at any time might become serious. Their appearance in a water, particularly a deep well water, from which they are normally absent, sometimes heralds the advent of pollution and enable steps to be taken in time to stop further pollution, or if this is impossible, to protect the consumer by suitable treatment of the water. In general terms, the presence of fecal coli denoted recent and possibly dangerous excretal contamination which must be urgently attended to. The presence of saprophyte in an unrelated water suggests less recent contamination, which, though not immediately dangerous, is nevertheless sufficient to call for further steps towards obtaining greater purity of the supply. The presence of saprophytic in a treated water suggests either inadequate treatment or the access of undesirable material to the water after treatment. Thank you.